Yeah, yeah. Thank you very much for the introductions. And I just want to check if all of you can see my screen and slides.
Yeah, that looks great.
Yep. All right. Yeah. Thank you very much, everyone, for joining me today. So, today, I'll give a very brief, non-technical overview of multiple implementations in applied research. So, I'm Associate Professor Gary Chan, and Sophia has already given instructions. So, I have a few research area in substance use and addiction epidemiology. My main research focus at the moment is on e-cigarette use in young people and also game addictions. My I have trainings in mathematics, and then I switch into some biostatistical research as well. So today I'll give you a very brief overview about multiple implementations and what it is, and some very conceptual understanding of that. And at the end, I hope to encourage everyone to use this method more frequently because it's a very useful technique that can be used to reduce bias due to missing data. All right. So there are actually a few key references if you're interested in this area. There's a few key references you can look at. The first four are short papers that is about more recent developments and also some misconceptions about multiple implementations in applied research. The last one is actually a textbook on multiple implementations. And the second one is actually a very interesting read. It is give you some non-technical explanations about certain misconceptions about multiple mutations as a method of handling missing data. So I encourage everyone to look at that. But I can send these papers out at the end of this talk. So first of all, missing data mechanisms. These are something that we always need to check and we will need to know before any data analysis. I'm sure that if for those who have background in psychology, they might be very familiar with the first one, missing completely at random. And in psychology course, I believe that certain tests, like say for example, the MCAT-Little's test, has been used to see whether the data is missing completely at random. So what does it mean? So in this case, missing completely random means that the data are missing data are entirely independent of both observed and unobserved data. So when would this happen? Like for example, if you have some data lost due to records being accidentally deleted, in this case, you would be able to assume that the data is missing completely at random because like if you say, for example, a fire burned down your computer, that data should be missing completely at random, and you can actually do a test on that. The second one by its name is missing at random. That is a very confusing name for many applied researchers because like it sounds like that it's missing at random, uh, but actually it's not. Like so, the data MAR, if the probability of a value being missing depends on observed data, but not unobserved data. Like for example, there's a few examples that satisfy these criteria. So, for example, males are more likely to drop out in a longitudinal study. Like, say, for example, they're less likely to do follow-up. In this case, if you would already know whether a participant is male or female at the beginning of the study, right? So, so in this case, this is actually a missing at random scenario, MAR, because we can predict this missingness using data you already have in the data set. And in a longitudinal study, participants who were engaged in polysubstance use at baseline were more likely to drop out. And if you measures the polysubstance use status at baseline, in this scenario, it is also missing at random. All right, so the next one is not missing at random. Okay, so like nearly all the statistical method missing more modern missing data handling method can handle the first two scenario. Like multiple implementations, it's really good at handling missing at random. So like say for example in the CRE data, for example, like this is very common. In the second scenario, like if participants are lost to follow-up because they are at higher risk we already know that they are at higher risk of dropping out. Like for example, at baseline, if they have a severe comorbidity, we know that they are going to drop more frequently in the follow-up. And if you already measures all these comorbidity variable at baseline, missing multiple mutations will be able to handle that. The third one, not missing and random. This is the scenario that unfortunately no statistical method alone would be able to handle. So what is the definition of that? Data are missing, not random, if the probability of values being missing depends on unobserved data. So that's data that you were not able to observe, even after accounting for all the other observed variables in the data set. Like for example, in a longitudinal study, participants who were still using drug at follow-up are more likely to drop out. Okay, so like say in this scenario, because they already drop out, you would not be able to know whether they are still using drug, right? But that's something that we already know in research as well. Like if the participants are using drugs, they are more likely to drop out. So unfortunately, this scenario missing data stats, you would not be fully adjust for this using any statistical method without us making certain assumptions. Another scenario is that if in a longitudinal study, participants who were engaged in polysubstance use at baseline were more likely to drop out, but you forget to measure this at baseline. This is also a MNAR scenario, right? Because you haven't measured that. All right, so all the statistical methods we know now can handle the first scenario pretty well. The third scenario, there's some way to get around to that, but you will need to make some assumptions that a lot of time is not testable as well. So multiple mutations can handle the first two scenarios without any problem. So multiple mutations can improve statistical power under MCAR, so missing complete and random scenario, because you don't have to drop any data, and can eliminate bias under the MAR scenario, which is missing and random scenario, theoretically at least, provided that the imputation model is correctly specified. So like you include all the key informations in your data that can predict missingness. However, MI is also likely to reduce bias in the last scenario, missing not at random. Like for example, I'll give you more example on that. Like for example, in a longitudinal study, like so in this scenario, let me see if I can get a laser pointer. So in this scenario, in a longitudinal study, participants who were still using drugs at follow-up are more likely to drop out. Okay. So, however, if at baseline you have some measurements of, like say, for example, severity of drug dependence, severity of drug addictions, for example, that is a variable that can predict substance use at follow-up as well, right? So, if you adjust for that, you can kindly reduce that bias because you have some predictors of drug use at follow-up. And also, like for example, in the second scenario, in longitudinal study, participants who were engaged in polysubstance use at baseline were more likely to drop out, but you forget to measure that polysubstance use. However, if you measure like certain drug use, like for example, methamphetamine use, then even though you haven't specifically measured polysubstance use, you will still be able to reduce the bias due to missingness because we know that participants who use methamphetamine are very likely to engage in polysubstance use in anyway. So you can partially adjust for that. So that's why multiple mutations, even in the first scenario, MNAR, it's very likely to reduce bias due to missingness. And I know that there are some of you have asked questions about other technique, like say for example, full information maximum likelihood estimations. That technique can also address the first two scenario. However, I would say that multiple mutation is a more superior technique in a way that it can handle a lot more scenario. Like for example, full information maximum likelihood can only address certain statistical methods. For example, like structural equation modeling and it's very highly dependent on the software you use as well. But for multiple implementations, you can because you are imputing the data. Once you get the inputted data, you can use any software to analyze that. You can use any models to do that. So it's more um, software independent. So to give you a very uh, quick overview, non-technical overview of why it works, I I use these examples like based on observed data, multiple permutations make an educated guess of the missing data. Like for example, we know that male are more likely to use drugs. If we're measuring polysubstance use to follow-up, we know that male are more likely to use polysubstance use, engage in polysubstance use. We also know that people who engage in polysubstance use at baseline more likely to engage in polysubstance use follow-up anyway. You can estimate these associations within the data, within the available data in your data set, right? So like for example, this is our data. We have like these participants have missing data at follow-up. But we know that this is a male, this is a polysubstance users at a baseline. So if we are going to make an educated guess, what is the polysubstance use status at follow-up? We're very likely that we'll put a yes in that box, right? If we have a female who are non-polysubstance user at baseline, if we are going to make an educated guess, we will say no in this case, right? And so you by now you might ask why we need to do imputation more than once. In we can just make we if we just want to make an educated guess, because we would also need to account for the possibility of errors in making these guesses, right? So like if you just make one single guess and do analysis, you're actually treating your guess and actual observations, right? So that is treated as actual observations. In that case, you ignore the possibility of an error. So like you might that would introduce bias as well. So now then we would make multiple guesses. Like for example, there could be some possibility that like for these participants who is male who use polysubstance use at baseline, he might stop. He might realize that that's a bad thing. That's very bad to his health. He stop use engaging in polysubstance use. Although that chance is not very high, so you will still make some educated guess based on that. So the principle of multiple imputation is that you just guess many times and based on what we know from the data. So like for example, for this participant, male polysubstance user at baseline, if you make 20 guesses, like you would 18 out of 20 times you'll guess this participant who will use polysubstance or who would engage in polysubstance use 18 out of 20 times in follow-up, but like very in an unlikely scenario, two out of 20 times, he might not be using polysubstance. For female, like this female at baseline, female and polysubstance are not using polysubstance at baseline. Very likely that these persons she would not be using polysubstance at follow-up, like 14 out of 20 times. But you never know. Sometimes it happens 6 out of 20 times, like of the educated guess, there could be some chance of polysubstance use at follow. So like the chance here, like these educated guess would actually be based on the data structures, based on the full information, all the informations in the data set. So that's what the multiple implementations algorithms will pick up. So then the idea is that in the imputations models, like you specify all the variable that like in a that is important for making the guess. So this is a very non-technical explanation about what you need to do in when you do the multiple implementations. So, like say for example, if you know that like male, gender, polysubstance use status at baseline, comorbidity at baseline, all these variables could be used to explain missingness. Then you put that all these variables in imputation models. And it doesn't matter like whether the data is from future wave as well. Like for example, if you have like in a sense scenario, if you have multiple follow-up, say for example, baseline follow time one, time two, if you have participants who have missing data at time one, but you have some data from time two for that participant as well, you can use time two variable to make predictions of time one. Although like logically you would not make in an analysis model, you don't do that, like because like you don't use futures observations to predict past observations. But in a multiple imputation scenario, you that's completely fine because future observations can also make predictions, filling in missingness in past of observations. The rationale is that, like, for example, if someone who are using drug at time two, if someone is a polysubstance user at time two, and you don't know what happened at time one, if that person is a polysubstance user, it's very likely that he has a history of polysubstance use, and he would be engaging in polysubstance use at time one as well. So information in future are actually helpful for us to make an educated guess in the past as well, if we don't have the information. All right. Uh, And there's some very technical recommendations on how we use them, or how we do make these guesses. Like for continuous variable, ordinal or binary variable, predictive mean matrix. Like there's a button if you're doing that in SPSS, there's a button in SPSS that you can about asking you about what algorithms or what models you want to make the predictions. The predictive mean matrix is a very useful technique for making the educated guess for continuous variable, ordinal variable, and binary variables. Because it can, in non-technical term, because it can pick up some nonlinear relationships as well. However, for categorical variables, you use multinomial logistic regressions. Then, after using the imputation model to fill in the missing data, make 20, 30, 40, or 50 educated guess, then the principle of multiplication is that then you run the analysis models on each imputed data separately. This you don't need to do that manually anymore, like because most of the software can do that in one go for you. But this is what these software have done behind the scene. So it will run the analysis model separately for each of the imputed data. And then it will use some sort of algorithms to combine these data together, like the estimate together, to form a single estimate. So like usually these software would use something called Rubin's rule to make that combination to combine these estimates. So there's a few myths about M multiplications. Like for example, if the result from statistical analysis obtained from MI differ from those from complete data analysis, then the result of MI is wrong. Like this is a very common myth about that. If this is what happened, actually the result from MI is more trustworthy than the complete data analysis because like MI is supposed to reduce the bias from missing data. So it's very likely that if complete data analysis give you one set of result, MI give you another set of result. It's more likely that the result from complete data analysis is biased because we know that the data is biased because of the missing data. If you use MI to reduce that bias, that result should be more trustworthy than a complete data analysis. And there's also some myth about like outcome variables must not be imputed. That's also not the case. Predictors variable must not be imputed. That's not the case as well. Again, if these data are missing um, uh, because the missing data are biased, then multiplications by default would reduce these bias. And for those who are very interested in reading up more on this, in the technical details about that, they are very encouraged to read the full paper that I suggest up front. And another questions that is often asked by applied researchers is how much is too much. Like say, for example, like when researchers see that there's like 20, 30, 40% of the data is missing, they are hesitant to use imputation method. And actually, if you have 40% of the missing data, you should use multi-imputations more because like if you do complete data analysis, it means that it's very likely that they are missing data bias that you haven't addressed if you use complete data analysis. And more recent data simulation study based on missing data analysis and multiplication suggests that multiplication can handle extreme high level of missing data. And what are the breaking point? For example, the more recent study demonstrate that uh, um, multiple imputation is very robust and it doesn't mean that it doesn't break. It would break. Like for example, if you have small samples, if you have a very small sample size that is like less than 1,000, an extreme high level of missing data, more than 90% missing data, then multiple imputation will break. But like if you have a large data set, like say for example, if you have a couple thousand of participants and you have 40% missing data, like multiple implications should be able to handle that without any problem. Like say, for example, these two studies demonstrate that, like especially this one, the one on the right-hand side, it conduct simulation study, like say, for example, generate new complete data and then randomly or like simulate a missing at random scenario, and then they test what would happen. Like for example, like the model only break if they have a small sample size. And if they only have 80% of missing data, it will still be able to address the bias due to missing data. So I know that like some of you like Nina and other colleagues have asked me about some code for doing missing data analysis and also implementations in R. I have to say that I don't do these type of analysis in R very frequently anymore, but I just dug up some code some code from some very old slide that I did in back into the 2020. And then like say for example, these are some code that would work. Say for example, now you have a data set like this, peer drug, like say for example, you want to predict illicit drug use in adulthood, but you have based on some longitudinal data where you collect data multiple time, wave time one, time two, time three about peer substance use. You collect data about gender of the participants. You collect data about antisocial behavior of these participants at time one, two, three during adolescence. You collect data about cannabis use, for example, and you want to predict illicit drug use in adulthood. What are we going to do? So like these are just like some example code that I'm more than happy to explain if you have further questions about that. Like for example, the library we use for multiple imputations in R is called MICE, multiple imputations through by chain equations, MICE. And then there's other library called MI tools. By now there are other library that can do multiplications in R, but these are the two very popular options. And then you can use the default setting, but you can also clearly specify how you're going to impute the missing data, missingness. Like for example, you would need to make the formula for predicting missingness in each of the variables. Like for example, this is very simple. Like it should be self-explanatory. Like for example, you want to predict the missingness in the first variable, antisocial behavior at time one, antisocial behavior at time two, and you want to specify what variable you're going to use to predict the missing data in that particular variable. Like for example, for antisocial behavior at time one, I want to use, this is just saying that I want to use um, antisocial behavior at time two, gender, peer substance use, peers at time one, two, and I actually can use the illicit substance use status in adulthood to make a predictions of what happened in the past, right? So these are the way you can specify the formula for each of these. And if in the data set you don't want to use like these variable, like say for example you don't want to use all these variable, then you just like don't specify anything, but like you will need to make it clear as well. Then these are some settings. You want these are settings that I say that I want to use the mice package to do the imputations. I specify the method, specify the formula. These are some fine-tuning settings. You can m equals 20. I think that setting does means that I want to impute 20 data set. Like, but ncore and nim.core, these are things that you can just ignore. Like you remove that. These are based on my computer settings. I just want to do parallel imputations like that make the process faster. And then you can plot the data, impute the data, and then these are the code for specifically saying that you want to do you want R to help you to analyze these 20 data set separately and then combine the result together. And these are the line of code that give you the summary. So I'll quickly show you what it looks like. For example, these are the plot from the multiple implementations based on this line of code, plot imputed data set. We will need to make sure that the imputed data there would not be problem in the imputation algorithms. So how can we tell is that, like say for example, once you plot that, if this line doesn't show any pattern, it look all mixed up, it's good because it means that the algorithm doesn't like stuck at certain stage. So like all these looks very good. Like just look at the mean, it's fine. You don't need to worry about the standard deviation too much. And then the second line of this line of code, running the models and do the summary, just give you this table. Like these are the estimate, which is the odds ratios. You also have the p-values and also the confidence intervals here. Like say, for example, in the model, what I did is that I say that now in the analysis model, I want to look at the association or make the predictions based on antisocial behavior at time one, antisocial behavior at time two, gender, peer, substance use at time one, peer substance use at time two, and I want to specify the logistic regressions by specifying the family as binomial, and I run these models. And the last line of code here is that just like saying that after running these, rest, store the result, and I want to pull all the 20 separate analysis into one single estimate. And I want to get the confidence levels 95%, and I want to get the odds ratios instead of the log odd from the logistic regressions. I'll just specify exponentiate to be true. Then you will have the odds ratios here. And these are the p-values. Like for example, we can say that like antisocial behavior for those who engage in antisocial behavior at wave 2, they are at 2.27 more likely odds of illicit substance use in adulthood, and the results are highly significant. And that's it. I guess that's the end of my presentations. Any questions?
Thanks, Gary. That was a really interesting presentation. And I think especially it's interesting to know that outcome variables can be imputed. I think there's a lot of debate that you see sometimes with people saying that it can't be imputed. But I was always under the impression that it could be, so it's good to get your confirmation on that. And also really interesting to see that up to like 90% of missing data can be effectively handled using multiple imputation. That's amazing. That's really good to know.
Yeah.
Especially, I think a lot of us working with real world data where there's, quite a lot of missing data, understandably.
Yep.
Um,
Yeah, of course. Like having said that, like of course, it can only work provided that you have a lot of variable that can
yeah,
predict missingness. Like, but like in your scenario, in the CRE data, like I believe that a lot of variable can can be used to make that predictions. Like for example,
yeah,
participants who are like as what I mentioned, like participants who are having a lot of comorbidity at baseline, they're most likely to drop out, right? So you already have that information. So uh,
yeah.
of course, like you can use that information to make the predictions, what would
Yeah.
happen moving forward.
Absolutely, yeah. So good to keep in mind that your multiple imputation is only as valid as the variables that you're using to impute the data
Yep.
after you've established MCAR or MAR usually. But also good to know as well that it works with reducing bias for M and AR. So I think a lot of the time you can get a reviewer that says, okay, you've got a lot of missing follow-up data. We know that people who use substances are more likely to drop out, then you've got MNAR data and, all those kind of questions around that. So it's good to know it reduces bias. Does anybody have any questions for Gary? You can ask them now or pop them in the chat if you'd prefer.
I just had a quick one and it's kind of two-pronged. Thank you, first of all, that was great. So I'm not sure if, and my logic might be wrong here, but if we impute more times and create more data sets, does that increase our confidence in the MI output?
Yeah, that's a very good question. It's like in at the very beginning when this methodology was developed in 1987, 1989, the recommendation is that you only need 3 to 5 data set. Um, Again, at that time, because computer is very slow, so imputing 3 or 5 data set would take a whole night, for example. But now I don't think that is a constraint anymore. Like you can easily like impute like 50 data set without any problem. So like I would suggest like yeah, 50, 60, or even up to 100 won't be a problem. So like, why not do that yet?
Yeah. And then with that, is there a confidence interval or something that we can, or that we should report in terms of how confident we are in the MI itself, or it's more just our confidence in the individual associations at the end?
Yeah, so as you can see from my slides at the end, you would have one single confidence intervals at the end, right, for each of the estimate. So that confidence intervals already combine information from multiple data sets. So like that handle that already.
Okay, cool. Thank you.
So I guess just following on from Sophia, you said that we could probably do 50 to 60 multiple imputations of the data sets. Is that kind of what you'd suggest doing? Or does it kind of depend on the data and the amount of missingness and everything? Or
Yeah, I would say that that's more of practical recommendations. Like 50 data set is more than enough. Yeah.
Okay, cool.
Yeah, I do see that people do 100 data set, but that could be overkill. But at the same time, it doesn't hurt, given that the
Yeah,
computer is so fast now, so you can easily compute 100 data set without any problem.
yeah, cool. Any other questions? Oh, Sean, I think you might be asking a question, but we can't hear you, or at least I can't. Okay, I think while Sean figures out his microphone, I might ask a quick question. Um, so with regards to longitudinal data, sometimes you have attrition across, the different time points, but then you also sometimes in the data have missing items. Do you need to treat those separately when looking at missing data mechanisms for, when you're conducting MI? Or can you look at them at the same time and just code anybody with missing data, whether it's attrition or missing data within a time point, as having missing data?
Yeah, again, the missing data only just depends on the missing data mechanisms. If the data is missing at random, like whether it's at item level or attritions because of the participant completely dropping follow-up, that's not like again, if you can classify it as based on the missing data mechanisms, that's fine. Like if they are dropping out of the study because of the missing at random mechanisms, or they have a particular missing data in one single variable in the data set, and if that is also because missing at random mechanisms, you could just like handle them together at the same time. So it's isn't no major issues there.
Okay, cool. That makes it nice and a bit more simple to look at the missing data. Okay, I think Sean's put his question in the chat. So Sean asks, can I use this method on unknown data?
What does that mean by unknown data? Yeah, because I guess it really depends on that. Like say for example, if you have 4 wave of data, and then say for example, the last data collections is collected this year, 2025, but you want to make impute data what would have happened in 2026, then that doesn't work because you completely have no information what would have happened in 2026. But like the idea is that like say for example if you want to impute data in 2025, but like you have 80% of missing data, like 80% of participants drop out, you have 20% of data from your data set. Then what this algorithm will pick up is that based on the information, all the informations you have from that 20% of the data and also previous wave, it can fill in the 80% missing data based on what we know in the data structures we are in the data set. But if you say that unknown data is like something that is happening far futures, that's not what this methodology is designed for.
Yeah, hopefully that answers your question, Sean, but let us know in the chat if not. Janie, are you asking a question?
Just following up. Just following up on Sean's question. Sometimes in the data we analyze, there is option like asking people, do you agree with this? And people can answer yes, no, or unsure, or don't know. And sometimes it's very small number or like not super high, then sometimes we try to make it missing and then impute it to make them as an option. But it depends on the research question because sometimes like people answering don't know, it could be an interesting outcome that we want to know, like why is it so many people saying don't know? And they are an important group according to our research question, then we don't want to delete them and make them say yes or no. We want to analyze them as an individual group. I don't know if you want to add to that, Gary.
Yeah. So like if Sean's question is about like what you have an option about not sure, like so I guess if not sure is actually important questions like response and like you don't do imputations, right? Like an example is that in my research area, like tobacco research, sometimes you ask like participants, do you think that vaping is bad for your health? And a lot of participants would say that not sure, don't know. That's an important answer by itself, right? So like you don't do imputations, you just treat that as a valid response in the response scale. And Brian, like so administrative data, you always use MI? Are there cases when I would say that it would be very rare that complete data analysis is the right approach because if you know that participants are are dropping out of the study because of some certain characteristic in the data, then multiple mutations would be able to handle that. So I think this is a questions that is very common in when in reviewers comment, like say for example, why you have 40% of missing data, why you do imputation. Imputation is not the you can't impute that much of data, but like the thing is that what are the alternatives? Like the alternative is only complete data analysis, which is have been demonstrated many times in the statistical literature that would be even worse. So I was the argument for that is that like it's right that multiple implementations is not the solutions that can handle every scenario, but for scenario that it doesn't work, complete data analysis usually produce the worst estimate. So that would be the argument for why I nearly always use multiple implementations to handle missing data.
Mhm. And Chloe also asks in the chat. Oh, sorry. Yeah, go ahead, Bryony.
Yeah,
So the next question is for longitudinal data. Is it better to impute missing data's follow-up period at the participant level
Sorry, Gary, just
or
quickly, I
at the
think
item
Bryony had a quick
level
follow-up
based on
question
the
as
available
well.
item score? So I'm not 100% that I understand the questions properly, but like I would say that if you are, say for example, if I assume that you are trying to ask whether like say for example, you already have a scale for like depression, for example, like should we impute the depression scale score or individual depression items? So in that case, if you don't have too many variables to impute, and then you have sufficient computing power, imputing individual levels items potentially would produce better outcome. But like practically, imputing this overall score would also work.
Right. And Bryony, did you have a follow-up question as well?
Yeah, I guess I was just reflecting, Gary, on, the idea that we do often know what's associated with, perhaps missing data at later data points, particularly, when you've worked in the sector a long time and you understand the data that you're working with and the population you're working with. But I can anticipate there may be students that are new to the area or working in populations they've not worked with previously, or it's an exploratory study. For example, I'm thinking of a project recently where we surveyed family members. So it's not a group that we're normally kind of talking to and surveying. And I guess it was just, are there any sort of tips or tricks or ways in which you might approach the problem when it's a new literature for you and you're not exactly sure whether the data are missing not quite at random, or whether they're missing completely at random, or indeed whether they're not missing at random? Yeah.
Yeah, that's a very good question. Like, unfortunately, like the missing not and random assumptions, that's something that you would never be able to test because by definitions, it means that it depends on something you haven't observed. Okay, so if students or researchers trying to some understanding of the data, so like what they can do is like, for example, for each of the variable, like you would have a missing or you will have whether variable about like information about whether that participant have missing data, yes or no, right? And then you can actually manually run some logistic regressions to use all the other variables in the data set to see whether you will be able to just predict missing data. Like say, for example, in my examples about illicit substance use in adulthood, for example, you don't need to immediately look at where the response. You can create a new variable about whether that participant have data or not having data in that variable, and then quickly run logistic regressions to look at, say, for example, whether peer substance use, antisocial behavior, attainment would be able to use to predict that variable, right? So like that would give you some indications about whether multiplications would work and can address that problem. And actually, that's something that I haven't covered in today's talk, but because I think it's a little bit more technical, because there's actually a metrics called FMI, fraction of missing informations, that you can look at to quickly have an idea about which variable would give you more information about the missingness.
Great. And another question from Sean that we have as well is with regards to the variables that we use in their multiple imputation. So some variables like age can be treated as continuous, so you can categorize people into different age groups. Is there one variable type that works better than the other in terms of continuous or categorical binary for MI?
Yeah. So in this case, I would suggest first of all, I will impute the data as continuous variable using the predictive min matching. Like predictive min matching has been demonstrated that predictive min matching is a superior method compared to using regression analysis to make the predictions. The rationale for that is that if you first impute at the continuous level, you retain most of the information. If you impute the age category, because there's some information lost in the process of categorizing variables, so that would lose a little bit of information theoretically, but practically, I feel from my experience, it seems the impact is very minimal. So ideally, and if it is not too much work, I would impute the continuous variable, impute the 20 data set, 30, 40 data set, and then afterward, I would use the imputed data to create the categorical variables.
Great, thank you. And May asks as well, as a follow-up to Bryony's question, if they were to use the mixed model MI using the mice package in R, what's the recommended cutoff point for the number of clusters for model stability?
Right. I would need to have a check on that because I'm not sure whether mice would be able to handle mixed effect imputations. However, in the past, the way I get around with that is that this is a time where imputations is not available for mixed models. You can actually treat the cluster as a fixed effect and do the imputations. Yeah, because provided that you have sufficient number of participants in each cluster. Like say, for example, if you have 100 participants each cluster, and then in that case, even if you have 100 cluster, 200 cluster, you can still do the imputations.
And I've got just a question from Chloe from before that might piggyback onto that question quite nicely. So when working with administrative data, especially if you've got clustered data, so perhaps clients clustered within different treatment services, sometimes you might have missing data within one particular service or, based on different client demographics. How do you treat that when you're doing multiple imputation? Because I guess it could be related to, client related characteristics, but it could also be related to certain services not collecting the data.
Then that would probably deal in the scenario where you have missing not at random because you have the data set is missing for the whole cluster, and then you don't have that, you don't have any information in that cluster, then you cannot make that unless you're willing to make assumptions that this cluster is very similar to another cluster, then you can draw data from another cluster to do the imputations. Otherwise, that you are in the missing not at random scenario where multi-imputations can potentially reduce bias, but you would not be able to fully eliminate the bias in that scenario.
And would you then just practically, if you're writing up the results, perhaps put in the limitation section that, you likely had missing not at random, you used MI, which reduced bias. However, you can't 100% confirm this given the nature of MNR data. Would that be the way you'd go about that practically?
Right. Yeah. You asked me to quickly address that. Issues, what I would do is, for example, if you have a lot of cluster, a lot of surfaces, you can do some sort of matching, right? So you look at, let's say, for example, you have surface A, surface B, surface C. You don't have any data from surface C at a certain time point, and then what you can do is you can use some manual matchings, or you use some algorithms to match that surface to see whether you can try find another surface that have very similar characteristic, patient characteristic with the surface that you are looking at. Then based on that, you use imputations. But then again, that is a missing not at random scenario where you're making assumptions that it is very similar to another surface, and then yeah, you do the imputations. So that's how I would address it. But you would, of course, I state that yeah, that's limitations.
Yeah. Okay. And another great question as well from Sean here. Have you encountered challenges from reviewers in the past when they were using MI, or have you found any papers, and what were your kind of concerns in terms of MI that you would give to authors?
Right. Yeah, this is actually very good questions, and that questions actually has been answered by one of the paper that I showed at the very beginning, where the papers talk about. Let me quickly pull that up. MIN. So it's from Sotero. So where is that? So can you see my screen?
Yeah.
So like this paper, like rebutting existing misconception about multiple imputations as a method for handling missing data. These all actually list out of a range of a challenge from reviewer in the past about missing data technique, and a few of them I've already presented, included in my presentation. Is that you say, for example, you have too much missing data, you should not use imputations method to impute that. But like that has already been rebutted by numerous simulation studies that demonstrate the robustness of our multi-imputations. Some reviewers say that like you cannot impute outcome variable, you cannot impute predictor variable, but like that has also been rebutted in the statistical literatures. I believe that most of these challenges are brought forward by applied researchers who are not very familiar with the technique. And intuitively, of course, we should not impute outcome variable, but like that's not how the statistical theory work. And that these theory has been solidly demonstrated to be appropriate based on a range of simulation scenario.
Great, thank you for that. It's good to have a particular paper that we can use in any kind of rebuttals if we do get reviewers kind of questioning the use of MI in some of our analyses. That's really great.
Yeah, and again, like I'm not saying that MI is a technique that can be used in every single scenario, but for most of scenario, if MI is not appropriate, completely appropriate, it can address bias, reduce the bias. And in scenario where MI is not appropriate, most of the time, all the other alternative would produce worse estimate. So that's why MI has been applied very widely in the statistical literatures. But I believe that there's still some quite a lot of hesitance in the applied community in applying this technique. But like again, a lot of these concerns has been rebutted by statisticians.
Yeah, that's great. Any other questions from anyone at the moment? I guess we're probably wrapping up soon, but I imagine a lot of people use SPSS or might be using SPSS to multiply impute their data. Do you have any kind of resources or anything that you could point us to in terms of applying it in SPSS? It's okay if you don't.
I don't have that out of my head straight away because I don't.
Yeah, that's totally fine. It might not be even a program you use very often, so not a problem.
Yeah, but I do have some resources on R, and also like Stata is completely no problem, because I would recommend using Status for this, because Status just make the number of code that you need to use for Status is much less than R and SAS and other program. Yeah, so that's why I prefer using Stata. But R is yeah, a very good program.
Yeah, good to know. And free, I guess, which is a big draw card. Cool. So any final questions or comments for Gary? Otherwise, we might wrap it up here. No? All right. Well, thank you, Gary, so much for an excellent talk today. Really appreciate it. I've been furiously making notes because I'm just thinking about how I'm going to apply this data to the papers I'm working on at the moment. So thank you.